Admit everybody.
Okay. All right, welcome everyone, and thank you for joining us today for our next installment of our webinar series sponsored by the United States Aquaculture Society, the National Aquaculture Association, and the Alabama Cooperative Extension System. Today we're extremely fortunate to have with us Dr. Claude Boyd, a noted water quality expert, who will be sharing some of his knowledge about aeration in theory and in practice. Dr. Boyd is well known for his contributions to research in the field of water quality and has over 50 years of aquaculture experience. He's logged countless miles traveling the globe and sharing his knowledge with farmers, universities, and government organizations. Dr. Boyd has authored hundreds of research articles and numerous books on the subject and mentored many students as well as faculty from around the world. I know we're all anxious to get started, but I wanted to cover a couple of pieces of housekeeping before we get started. Please remember to keep your microphone muted as we go forward, and if you have questions, type them into the chat box, and we'll try and get to them at the end of the presentation. In the coming weeks, you'll be receiving a survey about these webinars and their impact and their benefits to you, and also give you a chance to provide input for future webinar topics. So please take the time to fill that out when you do get it. And without further ado, I'm going to turn it over to Dr. Boyd, since that's why everybody's here. Dr. Boyd, it's all yours. Take it away.
Okay. Well, I'm pleased to be able to speak with you. It's a little odd not having people out in front of you there where I can see you, but that's the times we live in. And so I want to get started here with it.
Okay. Dr. Boyd, if you want to, you can turn off the camera now, and then we'll just be on the screen.
Do what now?
You can turn off the camera like we talked about, and then you'll just be, on the, there you go.
Yeah, but they wanted fans on here is the problem.
Okay, hang on.
Get it? Looks like it's not advancing. I was using it down. Is that what you were using? Yeah. I couldn't use this thing. There you go. Sorry about that. We couldn't get up the slides to thing. But aquaculture has really become a production method for animal protein that's based mostly on the application of feeds. So feeding has become very common practice to allow greater production than possible from natural food organisms. And this feed, even though it greatly increases production, it's not all used with the fish, a relatively small amount of it's actually used with the fish, because that feed that goes in is mostly dry matter. It's about 90% dry matter. And the fish that you take out is only about 25% dry matter. So, if you get an FCR of 1.5, that's fine from an economic standpoint. But from a water quality standpoint, that's untrue. It's, it's much more waste going to the water. Much more of the feed goes into the water as waste than goes into the fish to produce biomass. And if you increase those feeding rates very much, the water quality in the pond deteriorates to the point that, the fish are suffering from oxygen depletion, and they're more susceptible to disease, and they even die. And with most species, somewhere feeding rate above 30 kilograms per hectare per day, you're going to need to either stop feeding and not feed anymore are to aerate. And tilapia are a little exception to this because they're tolerant to low oxygen, and maybe twice as much feed could be used, or even more, but they are more tolerant to oxygen than most others. So the feed is, this kind of shows the fate of the feed. The feed goes in, and part of it's not eaten. Now that uneaten part is much larger for shrimp than it is for fish. Fish, you know, virtually all the feed, if it's fed properly, will be consumed. The shrimp nibble, and they probably lose, you know, anywhere from 10 to 20% of the feed just ends up entering the water and never being eaten. And so the part that's actually absorbed by the culture species, part of it is excreted as feces. That's probably another 10 or 20%. Then the remainder is absorbed across the intestine, and then a lot of that is excreted as ammonia and CO2 across the gills, and only a portion of it ends up harvested in the culture species. And then of this waste that goes into the water, well, one portion of it up there that came from the uneaten feed feces is still in the form of organic matter, so it's broken down to the bacteria. And then the part that's excreted by the fish, you know, it's mainly ammonia and CO2 and phosphate and a few things like that. And so the microbial decomposition of the organic matter then produces ammonia, carbon dioxide, and phosphate. And this ends up in pond systems, at least, causing more phytoplankton production, and they die and use oxygen, and the nutrients are recycled and so forth. I think most people are vaguely familiar with this, but what I want to point out about a couple of things here about aeration. In the first place, fish and shrimp have a unique problem with, well, I would say unique. Any kind of aquatic animal has a problem with respiration compared to a land animal. You know, you can calculate, I won't get into the calculation for you, but I'll tell you what it comes out. If you wanted to expose the respiratory surface, or the alveoli and the lung of the land animal, to what comes in contact with the gill of an aquatic animal, the amount of oxygen, the weight of water that has to be pumped across those gill membranes to expose that surface to 1 gram of oxygen, or any quantity of oxygen for that matter, would be 253 times more than the weight of the air to expose the same amount of oxygen as land animals. So for that reason, you know, oxygen is a very important limiting factor in the production of aquatic animals, and especially when, you know, stacking them together like in a feedlot situation. You know, you put animals in a feedlot and you don't have to aerate, you know, just the natural circulation of the air brings it, replaces the oxygen that's used up in respiration and gets rid of the CO2. But in the pond, that's not quite so simple. The water doesn't circulate near as well as air. The other thing that people don't seem to understand a lot of times about aeration is most of that oxygen that's provided by aeration doesn't end up being respired by the culture species. Most of that oxygen goes for the oxidation of waste in the system. So you have to understand that about aeration. Just when you put aeration in, if that aerator transfers a kilogram of oxygen to the water, well, not near a kilogram of oxygen is available to the fish or the shrimp. Now you could come up with, you know, I think most of you are familiar with the biological oxygen demand, and that's the amount of oxygen it takes to oxidize the organic matter in a waste. And you know, you can think of the feed as having a BOD if you want to, and the BOD would be the amount of oxygen required to oxidize the organic carbon and the nitrogen applied to the pond or to the other culture system and feed, but not recovered in the biomass at harvest. And you know, but what I mean by oxidizing nitrogen, these fish excrete ammonia, then the bacteria, some of the bacteria in the pond, the nitrifying bacteria oxidizes ammonia to nitrate, and that takes a lot of oxygen. And the organic carbon is converted to CO2, and that takes quite a bit of oxygen also. You know, there's the oxygen to carbon ratio. It doesn't matter who's doing the decomposition, whether it's fish, shrimp, bacteria or people or cattle or whatever, that's going to be the ratio of oxygen to carbon, organic carbon in respiration. So if you put a kilogram of carbon that gets respired away, that's going to take 2.67 kilograms of oxygen. And for nitrification, there's a summary equation for nitrification there, the ammonia plus water. It's carried out by bacteria, of course, but that ratio is 4.57. So for each unit of ammonia, of nitrogen and ammonia that's nitrified to nitrate, it takes 4.57 units of oxygen. Most of the oxygen is required for oxidizing carbon because there's a lot more carbon in the waste than there is nitrogen. But that equation right there would give you the BOD of feed. If you took the amount of carbon in the feed and subtract off the amount of carbon you harvest in the fish and multiply that times 2.67, and you take the nitrogen in the feed and you subtract off the nitrogen in the fish and multiply that times 4.57, that's the BOD of the feed. If all that waste from the feed gets oxidized. And there's some values for what would be the BOD of feed. The assumption is that the feed's about, in this particular calculation, is that the feed's about 45% carbon and 5% nitrogen, and the live fish are about 12% carbon and 2.5% nitrogen. Now, the values would be slightly different if we had some other concentrations of carbon and nitrogen in the feed or the fish or the shrimp. But that's roughly what you would get. And you see as the FCR increases in the pond, the more the feed BOD per pound of feed. But the main thing is, the more feed you put in, the greater the oxygen demand. That's the only point I want to make here. Now, in wastewater engineering, when I first figured out you could calculate this feed BOD, I thought, well, that's nice. You can take that and do like you do in wastewater engineering and calculate the amount of aeration you need. And I'll follow up on that in a minute because that doesn't turn out to be the case. But in a pond, the more plankton you've got in the water, the more dissolved oxygen you have in the daytime, but the lower the dissolved oxygen goes at night. I think everyone's seen curves like that. So as the plankton bloom increases, or as the waste load in the pond increases, you have a greater rate of photosynthesis, but you also have a greater rate of respiration. And the oxygen demands go very low in the morning where there's a lot of waste going into the pond or a lot of plankton in the pond. And of course, in some of these heterotrophic systems, the plankton basically disappears. It's all replaced by bacteria, and then aeration is the main source of oxygen even in the pond. And this is just a picture I had there. One of the students here one time around the aerator at the end of a catfish pond over in West Alabama. And you can see that's like soup. That water there is just full of plankton. Drifted up in that corner. But all over the pond, it was almost that thick. So the plankton blooms in ponds get awful dense. This is an old slide we did from years ago, but I assume things haven't really changed much since then. But along the y-axis of that slide, the x-axis of that slide, we've got the feed input per day up to 50 kilograms per hectare per day. And on the other side, on the y-axis, we got the dissolved oxygen concentration in the early morning and the second visibility. And you see as the feeding rate increases, generally the second visibility decreases, but also the dissolved oxygen concentration don't decreases. And once you get past about 30 here, the concentration of oxygen begins to get something, the feeding rate beyond about 30 kilograms per hectare, the concentration of oxygen becomes low enough that it begins to stress the fish. During the day it's higher, but the fish get stressed in the early morning. The they don't feel like eating as well the rest of the day, even though there may be plenty of oxygen there. Now, some farmers use water exchange to try to flush out the waste. And of course, if you have a high enough rate of water exchange, you can do that. But unless you pump 25 to 50% of the pond volume per day through the pond, you're not going to have much success with the water exchange. And water exchange may be necessary too in some shrimp ponds to avoid high salinity in the dry season or in areas where the farms are in an arid climate. And in some types of cultured ponds and raceways, of course, it depends on high rate of water exchange. Now, some of these raceways may have several exchanges per day, per hour, or per day, or even per day, but some even 2 or 3 exchanges per hour. So water exchange is widely used in aquaculture, but it's not nearly as effective as aeration as a general rule. Now, people should monitor dissolved oxygen in their ponds just to make sure they've got enough. And I don't know what the best concentration is, but I would certainly say you don't want the dissolved oxygen concentration to drop below 3 milligrams per liter. And really not having it drop below 4 milligrams per liter would be good. But of course, in some marine systems for shrimp, I think you'd have a hard time preventing it from going below 4. It's even hard in freshwater systems to prevent that. But unless you just really over aerate the ponds, you know, if you have enough aeration there to prevent it from going under 4 at any time, then there's probably times when the pond's going to be greatly aerated. So it's a little hard to know what to pick as a minimum concentration. I did see a study done once where they had a number of species of fish. The US EPA did it, and they kind of concluded that when the oxygen got under about 50% of saturation, most species of fish didn't grow quite as well, but you didn't get any real big effects till it gets on down, you know, maybe to 25 to 30% of saturation. And in unaerated ponds, this exchange of water is intended both to flush out waste, but it also, you know, if the water coming in may be a little bit higher in oxygen, so you get some oxygen from the water exchange, but generally not so much. But if you can flush a lot of water through, sometimes that can prevent fish from dying. I know in the old days before we had aeration here on the fishery station at Auburn, when they'd have an oxygen depletion in a pond, they'd get a big pump and pump water from one pond into the pond that had the problem and try to provide enough oxygen for the fish in a zone there. But water exchange is just generally not very effective for maintaining oxygen. Now, this is some work that Les Torrance, that used to work at Mississippi State University, did. This was for channel catfish, and I think the same curve would apply to most warm water culture organisms, except for maybe tilapia would be a little different. But on the x-axis, on the y-axis over there, he's got the food consumption as percent of the high DO control, you know, where you have the most oxygen. And you see, if the oxygen concentration, the minimum oxygen concentration in the morning is there between 2 and 3 milligrams per liter, or parts per million, you don't see much difference in food consumption than you would if it maintained 5 milligrams per liter minimum in the pond. So it's kind of on that data there that I base that conclusion that if you maintain oxygen above 3 milligrams per liter, in a catfish pond, it's okay. In shrimp ponds, probably, you know, shrimp have a similar oxygen requirement. Most warm water species will. Like cold water species, you're going to have more oxygen. Probably only going below 5 milligrams per liter for cold water species. Now this is this is not a FCR that's based on putting a feeding ring in the pond and taking out the uneaten feed. This is just based on what happens when you feed the fish like they're generally fed commercially. And when we tried to publish this, they wouldn't let us publish it because we claimed this was the FCR. We said, well, this is what farmers do. They put it in there and they don't take it out in the feeding ring, but the journal insisted that they had to be based on what the fish actually ate. But, you know, putting that all aside, I'm going to show it to you anyway because that's what a farmer would see, you know, because they don't use a feeding ring to take that feed out. As the early morning deal concentration increased, you see, we got a better feed conversion pattern. See those ponds that had early morning dissolved oxygen concentrations of about 3 milligrams per liter and greater had the best feed conversion. Now here's some data of shrimp yield where they managed to have different early morning dissolved oxygen concentrations between 2.1. See, it was set up to try to maintain 2, 3, and 4, but it couldn't quite be achieved. Got 2.3, 2.96, and 3.89 is the average, and you can see the survival and the shrimp yields in the FCR. And that's not a particularly good FCR, even at the high oxygen, but this was done a long time ago, and wasn't as much known about feeding shrimp. But anyway, the principle you can see in this study, that if you maintain better oxygen, you'll get better yields and better FCR. And this is some similar data with some tilapia where they had to maintain some of the ponds around 10% of saturation and others around 30% of saturation in the morning. Had a control where the oxygen just dropped however low it would drop. They all had the same stocking rates. And you see the fish tended to be bigger as they had more oxygen, but there really wasn't much of a difference between 10% of saturation and the control. So you can see from this that tilapia are much hardier than the other species I've been talking about. Because, you know, that channel catfish data that Torrance had, probably around that 3 milligrams per liter is probably on up around between 30 and 40% saturation. Now, if you don't believe that other things use most of the oxygen, I hope I can convince you here, because these are some calculated oxygen, nighttime oxygen budgets. Of course, these are channel catfish ponds. This was a 12-hour night. And the first part of that's available oxygen. And in the water column at dusk, you would have about 100 kilograms per hectare. And the diffusion from the air during the night would give you an additional approximately 10 kilograms per hectare. And that's a total of 110 kilograms per hectare of oxygen. Well, the demand for oxygen for the fish, you see, is only about 60 kilograms per hectare. You know, this is a high standing stock of fish, 15,000 kilograms per hectare. The water column respiration is around 120, twice the fish. That's the plankton and the bacteria, zooplankton, and, you know, phytoplankton, zooplankton, bacteria in the water column. The sediment respiration is about 42, I'm sorry. And the total is 222. So there's a deficit there of 112 kilograms of oxygen per hectare for the night. And that means that you're going to keep those fish alive, you're going to have to supply that oxygen with a mechanical aerator, or they're going to die. Now, I thought when I first figured out you could do that calculation of the VOD on feed, that we could take these wastewater engineering calculations where they know in a wastewater treatment basin how much the waste load is. You know, these things are lined with concrete. They just dump the sewage in there. There might be some sediment at the bottom, but they keep it stirred up pretty good in those systems, you know, so it doesn't accumulate. And so they can calculate how much oxygen is being used per hour. Those things are actually measured. And they can estimate from the performance of the aerator that they've done in tests how many horsepower aeration they need to supply the amount of oxygen they need per hour. So we thought we could do that with ponds, but it turned out you can't do it. It's just impossible. The amount of aeration cannot be calculated from the hourly oxygen demand, and the Aerator SAE, that's the standard aeration efficiency. I'll mention what this is in a minute. This is done in wastewater because the oxygen demand varies and it's virtually impossible to measure in aquaculture ponds. Usually 1 horsepower aeration is enough for about 400 to 500 kilogram increments of fish or shrimp. And for tilapia, maybe 700 to 800. I don't really know. I've never seen that worked out for tilapia. So what you can do is you can figure out how many fish you want to produce. And you kind of know what the biomass is going to be at the end of the crop. And if you want to put all the aerators you're going to need during the grow out period, at the end of the grow out period, in at once, you can put in about 1 horsepower of aeration for every 400 or 500 kilograms of fish or shrimp that you expect to produce, or if it's tilapia, some of these. Well, now you're not going to need all that aeration all during the season, so you can't just use part of it at first and later on you stage in more. You run all those aerators from the beginning, you're going to waste a lot of electricity because they're going to provide more oxygen you need. So the dissolved oxygen monitoring allows the aeration rate and the time of day of aeration and so forth to be adjusted. So let's say a little bit about aerators. There's really 2 ways by which these aerators transfer oxygen to the water. One, they splash the water up into the air, and the other one is they release bubbles into the water. When you splash the water into the air, it spreads the water out, so there's more surface for the oxygen to enter the water. The aerator can't put any oxygen in the water. All they can do is splash the water up into the air. And then these diffuser systems that produce bubbles, well, the oxygen concentration in the bubble is higher than the air, so the oxygen in the bubble diffuses into the water. So the aerator didn't really put anything in there, it just releases air into the water, and those bubbles increase the surface area so you get more diffusion into the water. So those are the 2 basic kinds. They do have these pure oxygen systems, but it's really hard to get a very good efficiency out of them in a pond. And some these indoor culture systems, you can do a better job of that, but not out in a big pond. And I wanted to mention here the driving force of aeration is the difference in the oxygen concentration of saturation and the oxygen concentration in the water. So you can see from this slide that the aeration is much more efficient at 0 oxygen. Of course, all your fish are going to be dead then, or your shrimp. So you can't operate it down there. You're going to have to operate it up here somewhere around 3 parts per million. And you see there, the aerator is only going to be operating maybe 50 to 60% of its efficiency that they have in these tests, because at the test, the oxygen transfer rate is calculated at 0. And so you see, the closer that curve becomes to saturation, the slower the aeration rate is. So with aeration, you just really need to try to raise the oxygen up to 5 to 6 parts per million, because that's where the aerator is most efficient. And when the pond has more oxygen than that in it, you can turn the aerator off usually, especially in these green water ponds. That's not true in the bioflop systems. So you need to pay attention to the oxygen concentration in staging the aeration. So in terms of the types of aeration, there's gravity aeration, where you just use gravity to aerate the water. The trout raceway is a good example of gravity aeration. Those raceway units go down the slope. The water falls from one to the other, and in that white water zone there where the water is falling, we get some re-aeration because of the surface area of the water is increased there by falling over that weir. here's where they're using well water in a hatchery, see, and they're running the water through a screen there, and it's falling through the screen and being aerated as it goes down. Where you pump water into a pond and release it, you can put one of these alfalfa valves like this on there and restrict the flow out the end of the pipe so that it has to splash out to the sides, and you get some degree of aeration, but not a whole lot. But aerators are made to splash a lot of water into there. That's a simple type that's quite popular in Asia. The Taiwan style paddle wheel aerator. They're probably the most widely used aerator in the world, but they're not very durable and they're not very efficient. They drill all those holes in the paddles and that messes them up, and you can't convince anybody of that. But, you know, the water passing through that hole causes a lot of friction. And they've got too many paddles around it. It's got a lot of problems, but it's the most widely used aerator in the world because it's so cheap. It's really cheap. You know, you figure over a long time a better quality device is better. And then there's some aerators in the U.S. that are just used for emergency aeration. These great big paddle wheel devices that run off power takeoff with a tractor. There's a number of different forms. You know, these are some of the original ones up there at the top, and down at the bottom are some of the newer versions. But they splash a lot of water. Air, they can prevent a die-off, but it's awful inefficient. You know, the energy from the tractor is powering that thing is not used very efficient. This is some aerators they use in Asia. They got many variations of this, but you know, there's a motor up here on the pond embankment that you really can't see. That way you can see that down here, but nah, you really can't see it. But there's a motor up there that and a jack shaft mechanism to slow down the output speed of the motor, and this goes down this water pipe, see it connected there. They splash the water like that. Pretty inefficient. You know, the construction's very cheap. So they don't have bearings. They just put the shaft in those wooden slots there. But that's widely used. Here's some of the newer style, but still, you know, they're very inefficient. And they also have some underwater aerators in there, you see, trying to bubble air into the water. And over here, they've got a Aero 2 aerator. I'll show you a picture of that in a bit. Nah, I'm sorry, that's not what that is there. That's a sludge pump. They're trying to pump sludge out of the pond. We did a lot of work on mechanical aerators here in Auburn years ago because the farmers were wanting an aerator and they couldn't talk any of the agricultural engineers into working with them. And I finally was just kind of forced to work on those things. And so with the graduate students here, we did a good bit of work on these things. We got a torque sensor put in line with the aerator shaft and devised a mechanism where we could make all kind of changes in the shapes of the paddle. It's kind of a modular unit, put more paddles on and different arrangements of paddles and different kinds of paddles. We worked on that thing probably about 3 years. We probably run several thousand aerator tests. But we ended up designing a paddle wheel, and then the farmers took that design, well, not the farmers, but some of the machinists around took that design, and they figured out how to mount it on floats, how to connect the electric motor to it. It was a lot of things happened over the years. They had a lot of problems. We had a lot of problems developing the thing, but they had equally a lot of problems of trying to figure out what kind of motor and gearbox they could use, or whether it's better to use chain drives or belt drives or so forth. There's been a lot of work done on it. That's a very efficient aerator. There's a picture of something based similar to the original, although we didn't recommend that shape paddle. The paddle we actually recommended was the shape over here on the right. It has a 135-degree interior angle. But what it did was we recommended the whole 96 paddles, I think. This one over here had a bunch of the paddles taken out. So to make it cheaper. So I'm sure this one is not near as efficient as that one because that's paddle surface area. But there's one of them in the water running. But that type of aerator is quite efficient, although there's a number of other types of aerators, and I'm not trying to rank one over the other. This aerator here, we originally got some real high numbers for oxygen transfer, around 4 pounds, 4.5 pounds of oxygen per, it's in pounds, so they'll give you to per horsepower hour. And we later found out that the tank we initially did those tests in, I didn't get into this by my own intention. People wanted it done. And we used what we had available to us. And that tank wasn't quite big enough, and it resulted in us reporting a fairly a higher value than they really transfer. Later, when we got some better aeration tanks around, found out that it really was more like around 3 to 3.5 pounds of oxygen transfer per hour. It's still a lot more than those Asian aerators transfer. Then here's a type that some people use. It's a float with a submersible motor under it with a propellant on it. Jets the water into the air like that. One of the problems with aerators is everybody thinks, they're very simple, so everybody thinks that they can make an aerator, and once they make it, it's like they made it, it's perfect. And, you can look at that aerator and tell it's doing fairly well. I didn't put it in here, but I got another picture. They wanted to improve this aerator, so they put some kind of different kind of propellant on it, impellant. And now it throws water way up in the air, way up high in the air. And they brought it down here and wanted us to test it. I said, well, the old one's better. Oh, no, this other one, looks very pretty. It's throwing all that water up there. And we ran a test. The one that's throwing the water way up there transferred about 1/3 as much oxygen as the other. And of course, the reason is that it didn't pump near as much water. It just threw it up a lot higher. The water was just taking a joyride after it got about 3 feet high, and it wasn't taking on much more oxygen. So the problem is that most people that see aerators will pick the most inefficient one as being the most efficient because they're impressed by the fine spray or the water going way up in the air. And what you really want is an aerator that'll pump a lot of water up into this zone. If it's a surface aerator, up in this zone where it's transferring oxygen. And this is a propeller aspirator pump type. That particular one is this Aero 2 aerator. It's had a lot of use. It's a kind of efficient aerator. It's a different mechanism. What it's got is a rotating hollow shaft inside of that thing, and there's a diffuser down near that impellant, and the impellant jets the water forward, and there's a housing around that hollow shaft. It's got a hole in it up here near the aerator, and air is forced down in there by the atmosphere as that impellant evacuates the shaft. So it's an aspirator type device, and you can see the water comes out with air in it and very small bubbles. It's a fairly efficient device. This is some of them in shrimp ponds operating. You can see with the old aerators, though, you're going to see kind of what you see here, that the water's going to be going at a pretty good velocity right in front of those aerators, but the farther out you go, the slower the water movement gets. So these aerators create a lot of water movement around them. And I tell you, an aerator that sends the water forward, like a paddle wheel aerator or like these propeller aspirator pumps, are much more efficient in a larger body of water than one like that. Because you see, this aerator just pulls in the water around it. And pretty soon it gets a high oxygen concentration in the water all around that aerator. That reduces the efficiency of aeration as the concentration of oxygen in the water increases. But these aerators that push the water away from the aerator, see, they're always bringing in water behind them that has lower oxygen. So the efficiency of the aerator doesn't decline over time. And then these are the diffused-air aeration systems, and use an air blower to release the oxygen through an underwater diffuser. And the big problem on those things is that the water depth is usually not great enough for the hang time of the bubble to be sufficient to allow a lot of oxygen transfer. You know, they may only transfer 1 or 2% of the oxygen that's in the water. So those are not very efficient generally, but if you got a deeper tank, they are. But enhancers are very nice because you can use one device to power a lot of individual units. They're just not very good at pumps. And then these new jet aerators, they're kind of a variation of that Aerator aerator I showed you. They just have a Venturi device, and air is sucked down in here and mixed in this through this injector. And they eject the water horizontal to the pond bottom. That Aero 2 had to eject the water somewhat at an angle. These put it down at the bottom. So there's more use of that jet aerator now than used to be, but I think most of those devices are fairly expensive compared to the others. And the aerator performance test to see how efficient these aerators are is done in a tank of clean water, just usually municipal tap water. And you deoxygenate that water with sodium sulfide, and you re-aerate the water with the aerator that's going to be tested. And you measure the dissolved oxygen concentration with time while the aerator re-aerates the water in that tank. And then these results can be used to, I won't get into the details about this, but there's a mathematical technique for estimating the amount of oxygen that can be put into the water. And if you divide that amount of oxygen by the power of the aerator, you know how much. Well, it's calculated different ways. You can't calculate the power of that goes to the aerator shaft. The more commonly, they just count the power going into the motor, which is the wire power as opposed to the brake power, and report the SEC on the wire power. Sometimes they just report it on the horsepower rating of the aerator motor. But at any rate, just SAs usually reported in kilograms of oxygen per kilowatt hour, kilograms of oxygen per horsepower hour. And there's this equation I was talking about for calculating how much oxygen the aerator will actually transfer under operating conditions. I won't get into the equation, but where I solved the equation, you see if the oxygen was, there's some other, I won't go into those other, but there's some minor losses you get involved in there. And so I won't talk about those, but they have to do with things that are contained in the water that affect aeration rate. But if you had 0 oxygen and this aerator had been ranked in a test in clean water to transfer 1.15 pounds of oxygen per horsepower hour in the pond, it would actually transfer about 96% of this value. You know, about 96% of that. Wait, I told you wrong. I'm sorry. I didn't look at the figure. Say the aerator has an efficiency of 1.2 kilograms of oxygen per horsepower hour. See, I already made a mistake in this slide. I never noticed it before. That should be kilograms of oxygen per horsepower, okay? Sorry about that. It doesn't matter. You're going to have to change it one place or the other. You know, that was just an example, but I'm sorry about that. I never noticed it. But if it was ranked at 1.2 kilograms of oxygen per horsepower hour, then, you know, we got to have kilograms here. And so the SEC would be about 96, you know, the value was actually transferred to the actual aeration efficiency would be about 96% of the SAC, or you'd get about 1.15 instead of 1.2 and kilograms of oxygen per horsepower hour. And see, if you get down here to say 3 parts per million oxygen into water, it's only going to be transferring at about 61% of the SAE here. And so instead of transferring 1.2 kilograms of oxygen per horsepower hour, it's only going to be about 0.73. And see, the higher the oxygen concentration in the pond, the less efficient that device becomes. And when the water reaches saturation with oxygen, this was at 28 degrees centigrade, and there's the saturation concentration, it doesn't transfer any oxygen. And if the aerator, if the water has more than oxygen saturation in it, that aerator is going to become a deoxygenator and increase the rate at which aeration enters the air. Now they make devices now that you can put into the water that monitors the oxygen concentration, and it'll send a signal back to either start or stop the aerator. You program this all in, and what oxygen concentration you want the aerator to come on, and at what oxygen concentration you want the aerator to go off. And you can manage the aerator through this automatic monitoring system to prevent wasting electricity on aeration. So with aeration, you need to get the most, an efficient aerator. Not only is efficiency on an aerator important, but also its durability, what the service life of the thing is and what the maintenance requirements are, and once you decide on the one you want to use. Most of the aerators that have actually survived on the market are reasonably good. Even those Asian aerators work okay. They could be improved a lot, but most of them that have survived in the market at least do a fairly good job. And you just need to monitor the oxygen some way, either manually or with a device, so that you can learn when not to over aerate or not to under aerate. You don't want to do either one. If you under aerate, the fish will still be stressed. That's one of the main problems we have with aeration with most catfish farmers in the U.S. is they don't want to put enough aeration in the pond. They think, well, the aeration is just going for the fish. I guess is the idea. I'm not sure. I always told them, if you need to put more aeration in, but most people won't. They see the aeration just going to the fish, the oxygen just going to the fish, and they're thinking, well, if I put this aeration in there, I got to stop more fish. So what they do is they put the aeration in there, they put more fish in, and they're right back where they started, except they just got a lot more fish suffering than they did before. And so even though it allows big production, you're not getting very efficient production because the FCR is not as good, and you get a lot of mortality. Kind of the opposite problem happens in shrimp farming. I think most shrimp farmers, maybe it's because of the value of the crop, but they tend to, at least in Asia, use more aeration than they need. And then also maybe because in Asia, nobody ever monitors oxygen and they want to have enough aeration in the pond if they don't have low oxygen. But whatever the reason, there's been a fairly poor job of matching aeration runtime and aeration capacity in the pond with the biomass and that waste energy. And the energy for aeration in fish is, if you look at land use in aquaculture and water use in aquaculture, it compares, it's just about as good as, it's better than pigs and about as good as chicken, best way to put it, and a whole lot better than beef. But if you look at energy use, aquaculture uses a whole lot more energy than does the other types of animal production. Because of that is because we have to use so much aeration. Now, I've already explained why it has to be a lot of aeration. But then the other thing is that we really don't have to use as much energy as we're using because aerators are often not used properly. And so should be an effort to do several things. One is match the motor that's running the aerator to the actual aerator load. That's a particular problem in Asia where they use those foreign-made aerators. They don't match the motors to the load. Sometimes they've got a 14 horsepower little diesel engine sitting up there running a load that probably needs a 3 horsepower motor to turn it. And then in other cases, they may overload the motors. But there's a lot more effort to match the energy use with the actual need for oxygen in the pond. And that would reduce this high energy requirement for fish production. Another thing to understand in these heterotrophic systems, you don't have so much phytoplankton, so it's going to require more oxygen, but from aeration, because of the fact that there's not as much oxygen produced by the phytoplankton. And another thing is most of those heterotrophic systems, they put a carbohydrate source like sugar or molasses or something in the pond, and that has a big oxygen demand. And so you've got to add more aeration to that. So a green water pond is going to require less energy for aeration than will one of those heterotrophic systems. But the heterotrophic system gives you much higher production of the same amount of water. So it increases the savings on land and water, but it requires more energy. But we do need aeration has a major demand for energy, and we do need to increase the amount of energy used for aeration. Another thing I want to point out here is that aquatic animals' energy budget, you know, if you feed them, you get energy in the food, and you get energy out in feces, excretion, and digestion, and routine activity, and swimming, and then you have some growth. And the active energy is mainly the energy expenditure for swimming against the current. And that's a kind of a general equation that you can calculate for the amount of energy for swimming, and you see it's related to the velocity of the water. So the greater water velocity, the more energy the animal has to maintain, it has to use to maintain its position in the current. And so if the water, there's a water velocity where growth is optimum, fish is exposed to water velocity, fish exposed to water velocity greater than optimum for growth are often more physiologically fit and disease resistant. So, you know, making them swim against the current may have some benefit in the quality of the meat and for disease resistance, but also, you know, they may even taste better. But if you get too much water velocity, you know, they're going to have to spend so much energy against it, it's going to, you know, it's not going to be beneficial. And so we need some kind of balance among the optimal water velocity for growth, physiological health, and body condition. White-legged shrimp, there you see, they're affected by water velocities, negatively affected. Actually, they don't grow as well if water velocity is over about 5 centimeters per second. And the optimum velocity is calculated to be somewhere around 0.63 to 2.78 centimeters per second. And all this aerator design, you know, all I was ever involved in, we weren't really concerned so much with the water velocity. We were trying to get the maximum oxygen transfer. So we really need to kind of work out the best water velocity. That's just some optimal water velocities for several different species. Some can have a much higher optimum water velocity than others, but this has never really been considered much in aeration. And also, you know, when you put aerators in a pond, as I show in this slide, you know, the water velocities are going to be the greatest right out in front of those aerators. And if you put several aerators in the pond, and like if you had them around the sides of the pond and get the water to circulate, they're going to erode the embankments. And in this area where the water velocities are high, I'm not sure the numbers are big enough for you to see well, but you see the highest water velocities are out here around the edges in front of the aerators, and out here at the center, the water velocities are much lower, and the sediment accumulates out there, and that sediment becomes anaerobic, and the shrimp won't use that area of the pond. And then there would be some of these areas of the pond where the water velocity is too fast for the shrimp, and so you're going to restrict the shrimp into just a certain area of the pond bottom. So if you do, you know, if you have a lot of high water velocities and a lot of low water velocities in the same pond, that's the usual situation. The shrimp are going to pick out certain parts of the pond to accumulate. Let's just show a partisan shrimp out of a pond and look at that pile of sediment in the middle. They do better than that now. This is kind of a long time ago when I took that picture. That pond had a center drain in it, but they buried it, as you can see. But this is a water velocities in a pond with was about a 0.6 hectare pond, 0.56 hectare pond. It had 4 1-horsepower paddle wheel aerators. So you can kind of see the distribution of the water velocities. And this is with jet aerators. They seem to be a little bit better than the paddle wheels for water velocity, but not necessarily for transferring oxygen. There's the water velocity over the bottom of the pond aerator paddle wheels or water wheel aerators. See the area at the bottom is less than 5 centimeters, which the shrimp was kind of avoid because of sedimentations. 38% of the pond with the paddle wheel, and 54% with the water jet. Where the water velocity is too high, you see, it's especially greater than what is paddle wheel here. 4% of the area, but 39% was greater than 10. This is probably something we should pay better attention to in the future. So this is just about shrimp here. The shrimp, we generally avoid areas of water currents less than 5 centimeters per second. And they're sure going to avoid places where if it's greater than 5 centimeters per second, they're avoiding it because of the current. And where it's less than 2 centimeters per second, they avoid it because of sedimentation. Water velocities in aerated ponds range from about 1 centimeter per second, in some cases to over 100 centimeters per second. The erosion of earthwork usually occurs at around 7.5 to 15 centimeters per second. Sedimentation only occurs where the velocities are less than 3 centimeters per second. And what they've done in a lot of places is put plastic liners around the ponds, or at least around the sides, to cut down on the earthwork erosion. So that's about all I had prepared here. So if anybody has any questions, I'll be glad to try to answer them.
Yeah, Dr. Boyd, we've got a few questions for you.